Okay, hello everyone. This class we're going to continue our study of the computational methods in engineering, and specifically we're going to learn about the user-defined functions. So as a quick recap of our last class, last class we covered the input and output formats in MATLAB, right? So we introduced the input function or input command to pause the program and prompts the user to input certain value or string. We also talked about the display function, the formatted print function, the save print function, and the table function, right, to provide certain output under certain formats. And we also talked about the graphical input, the ginput function, where we can directly ask the user to take certain value from a plot. We also discussed about the file reading and writing, no matter whether they are text files or Excel files, or no matter you're exporting strings or values or matrix, right? Eventually, we talked about the code analyzer and debugging. So this class, we're going to learn about the user-defined function. So user-defined function, I would say, is very similar to the built-in function that's already available in the MATLAB, right? Remember, before we talked about the mean function, the cosine, sine function, all of these nice built-in function in MATLAB. But for a lot of the calculations or engineering calculations that we're going to deal with, actually, the functions that we're going to use, a lot of times they're not going to be built in. So we sort of have to create our own function by combining or using some of these built-in function. And we call these new functions as a user-defined function. User-defined function is very helpful for us to solve sophisticated problems. So you can create a database or basically a function base of our own user-defined functions and call them for your future tasks. Right. So basically, in the user-defined function, the first line in a function file must begin with a function definition line that has a list of inputs and outputs. So this line distinguishes a function M file or a script M file, because remember before when we talked about the new, right, when we create the script, if we directly type in certain commands, certain scripts, then that is a script M file, right? So for function M file, it actually starts with the word function. And then you could basically decide what the name of your function is. And also you need to specify what are the input values and what are the output values. So, and also pay attention that the output values, output variables are enclosed in the square brackets, while the input variables must be enclosed in the parentheses. And the function name here, which is the name, should be the same as the file name in which it's saved, the .m file. So for example, let's say we create a function called test, right? Let's say it needs two input variables, x and y. It doesn't have to be x and y. You could also use a and b, or let's say any value you want, or aa or bb, right? As long as you keep on using these variables inside the function. And then let's say it's taking the variable of a and b, basically two variables, and then it's exporting two results or outputs, right? We can name them as x and y. So pay attention here that basically a lot of times we don't use the same A and B here, because if you use the same value, same letter, basically it's going to export the same results that input into the test, input into this function here, right? We normally want to basically export the calculated results. So for example, we define a function that's taking A and B. So it's going to generate the result of x equals A plus B and y equals A multiply B. So now you have two outputs, right? X and Y. So let's just save this function as test. Remember, when you define a function, the file name has to be the same as the function name, which is the test over here. Okay, so now we just finished our function. It has the same name here. And then basically in the command window, we can start to use this function. So we can just name it, or let's say calculate what is the x value, right? You can do test. And then let's try 5 and 6. Okay, so as we imagine x will be 5 plus 6 is 11. Y would be 5 multiplied by 6, that's 30. So then this is what we get from this function, right? So we just defined our own user-defined function, right? And then we can use this function directly. And this is not basically the built-in function, because in MATLAB there's no meaning of building in such a function to calculate the sum and the uh, multiplication of like or to show both of these results, right? But it could be helpful for some of our specific tasks that we directly want the sum and multiplication results from certain variables. Okay, so this is our user-defined function, and we could also add in some information, additional notes here, right? So for example, this function returns two outputs, right? Um, the summation and multiplication, or the product of two input values, outputs, and then we can do X and Y and values A and B. Okay, so this is our notation here, right? So then you can try something. Basically, you can type in help test. This is, remember when we were using learning about the built-in function, we could use the help function, right? To learn about, for example, the sine function, right? This is what we're going to see. It has very good documentation, right? So you can do the same thing. We can do help test. So basically, this is what's going to return from the help, right? So you can see that what we type in as a comment right after the function name is going to be shown uh, in this help, shown as an output from this help function. Okay, so that's why when you create your own user-defined functions, try to include these specifications or descriptions of your functions so that we can directly access or get to know the meaning of these functions. Okay. So here are just some hands-ons for the function M files. For example, you can create a basically a function that returns the volume of a sphere, right? So you can do function volume equals volume sphere radius, right? So you can type in this function returns the volume of a radius, right? And then you will actually define volume equals 4/3 multiplied by pi radius to the power of 3, right? So also we might want to include a dot here, so just in case that people put in an array of the radius, right? So this is the basically the function, and then we make sure that the function name is the same as the .m file name. And you can see in this folder here, right? So directory, you can see this new function, and you could call it, right? So volume, we can, let's say, directly test X. Let's say we name the output as X equals volume sphere. And then let's try, for example, radius equals 10. Right? So then X is going to be equal to this value. You can directly call this function. It doesn't have to be, you don't have to use the same like volume as the output, right? So basically now you're just passing this value to X. And you could also try, let's say Y equals volume sphere. And then let's do 5. And you could also put a semicolon to, instead of using Y, let's use Z, right? So we define a new variable, and then here you have the semicolon. Basically, it's not going to display anything in the command window, but directly passing the sphere volume to the Z value, which is shown over here. Okay. So this is a sphere volume function, and we could also define, let's say, a function perimeter equals perimeter square side. And we know that basically the perimeter equals 4 multiplied by side, right? So we could, yeah, basically this is a function. We can save it. And then we can try, let's say, AA equals perimeter square. So this time, let's try an array, right? 1, 2, 3. Okay, so it's going to return you the perimeter. And you could also define your, let's say, the square root function, right? This is the square root, but I think there are already functions to calculate the square root, right? So you could define different functions that you want to, you would like to use. So Basically, we showed here that, I mean, the examples we showed earlier, they have one input, but as we showed over here, you could have multiple inputs being introduced into the function, right? So for example, here, let's just create this new function, the function z, right? Function z equals fun, x, and y. Okay, so then here we actually pass the x and y value into a u value, 3 multiplied by x, and we just want to see how the variables are involved or used in these functions. And z equals u plus 6 multiplied by y to the power of 2. Okay, so we use this dot here just in case people put in arrays, right? If otherwise, um, otherwise, if you directly use an array, let's say a matrix to the power of 2, is not going to calculate the right answer. Okay, so this is our defined function. And also, we should note that we use a semicolon at the end of the lines. This can basically suppress the display of the u and z values, just like over here. So if you do not use a semicolon, right, you can try basically x and y, and then it's actually going to show you the value of x and y. Okay, so eventually, basically these two x, y's are shown over here, right? So we use a semicolon to hide the output from the calculation. So it's the same thing here. And then we calculated z. So you can see that the x and y, which are the input value, are first passed to the u and then passed to the z. So then we have a question. For example, if you run, let's say z equals function 1 and 2. So is there a way to access the u value here? Because u theoretically to be 3 should be 3, but you can see that after you run this function, there's no u being shown in the workspace. And this is actually the advantage of the function. So whatever variable you named under this user-defined function is not going to be exported into the actual workspace unless you define them as the output, right? So basically, this is I mean, this is the advantage of using the user-defined function. So it's not going to occupy basically the space or the data or the room in the workspace. Okay, so you can call this function, for example, z equals function 3 and 7. So we get the same value here. And then you could also run, let's say run directly 3 and 7. Okay. So you can see that the result is 303, but as I said before, it's actually not going to pass the value to the z. So we can try another way. Let's say clear all the variables here and then try the function 3 and 7. So if you do the 3 and 7 calculation here, you can see that in the workspace, there's no variable of u and z, right? Because we didn't pass any value to these variables. So you can see that basically if you try to access z, it's going to say not recognizable, right? So this is mainly because if you do not directly put these values as output, there's no way we can access a variable inside the user-defined function. Okay. Yeah, so this is the whole thing is talking about these basically the definition or the usage of these variables. So basically these variables u and z are local variables, right? So basically their value are not going to be exported into the main command window. Okay, so unless you pass their value by naming them x and y, these values will be not available in the workspace outside the function. Also, the variable u is local to the function, right? So local functions or local variables are not going to have values assigned to the actual command window or the workspace. Okay. So also the other thing we should pay attention is that only the order of the arguments is important, not the names of the arguments. For example, you define this function as x and y, right? So you don't always have to assign x value to the function, y value to the function. Okay. So for example, you define x being 1 and then y being 2. So you have the x and y value. So basically, you can also run the function as y and x. Okay, because what matters is the value being put inside. So for example, if you use function x and y here, you see the result is 27. But if you use y and x, basically you put 2 as the value here as x, right? Because y originally is 2, right? So you put 2 as the value of x in this function, and you use 1 as a value of y in this function, okay? So then you're going to get the result of 12. So I would say that only the order of the arguments, right? Only the value of the arguments matter, right? Not the names of these arguments. Okay. So basically based on the definition of our function here, since we used a dot, right? So we could also run these functions by using an array, right? So one thing we just need to pay attention to is basically here the x and y should have the same dimension. Otherwise, we cannot add them together, right? So that's why if you run this function 2 to 4, that's 2, 3, 4, and 7, 8, 9, right? So each of them have 3 elements in their array. So then you can run it and you're going to get the result like this, right? So that's why when you define the functions, try to consider what the input you are going to use, right? If you use an array as an input, then try to include this dot calculation in your user-defined function. Okay, so as we showed in the result earlier here, right? So x and y both as the output. So the function may have more than one output, right? So we should include these outputs in the square brackets instead of the, let's say, the parenthesis here, right? So one example is shown over here. Basically, the circle function, right? We define the circle function that returns the both the area of a circle and the basically the circumference of the circle, right? So pi r squared, that's the area of the circle, and c 2 pi r, that's the circumference, right? So then we have two outputs, a and c here. So then we define this circle, we can basically assign these values. Let's say that we try to calculate for a circle with a radius of 2, right? So then we can name the output as A and B, right? So A is going to be the area, B is going to be the circumference. It happens to be the same because r squared is 4 and 2 multiplied by r is also 4. Let's try something different. Let's say we use 3. Then this is the area, and here this is the circumference, right? So then it may be that sometimes we may forget about these two variables because the user will not always know that there are two variables, right? For example, if you do the help of circle, right? So then actually it shows that there are two variables, but sometimes we may not, we may forget that there are two variables. Let's say we just assign these to a single value of a, right? Or to AA, right? Circle of 3. So you see that the AA is actually the first output, or which is the area. Okay, so the circumference is not being passed into AA, right? This is mainly because here we defined A. Let's say that there are two outputs. Basically, there are two outputs inside the circle, right? So then if you do not assign, let's say, the second output as the result from the function, then it's only going to return you the first output. So it's similar to, let's say, the function of the max, right? So if you recall, for the max function, you could directly run 1, 2, and 3, right? It's going to give you the max result from this array. But at the same time, if you check the max function, it can also export, right? It can also export the location, the index of the max function, right? So for example, if you still run the same thing of the max, and then let's say that now we force the function to give us two outputs, A and B. Okay, so you see that the index is 3, right? So the maximum is 3, the index is also 3, right? Number 3 of this array here. So what I'm trying to say here is that unless we force the function to give us the multiple outputs, then if you use only one variable as the result from the function, you're only going to get the first output from the function that has multiple outputs. Okay. So this is some practice over here, and then you can see that if you only use A here, right, one variable as the output, right, then you're only going to get the first output from the function. Okay, so we show that the functions may have multiple inputs, may have multiple outputs, but the function can also have no output, right, or no input or no output, right? So one example could be this function. So this function doesn't need any output, doesn't need any input, and doesn't have any output. So we can directly copy and paste over here. And then this is a show date function. You can see inside the date function, it clears everything, it cleans the screen, and then it's just going to call the function of date, right? So, and we also didn't use a semicolon, which means that the result of this script here is going to be shown in the command window, right? But we didn't define that as an output of the function, right? As you can see, it didn't have a square bracket or the equal sign, and also didn't need an input, right? So a lot of times when you define a function and then let's say the goal is to generate a plot, right? So the plot, when you create a plot function, let's say plot, let's just output some random numbers. Okay, so the plot is not an output either because that's not being shown as the left side of this function. We didn't use the equal sign in the function, right? So there's no output and also there's no input. So now if you run it, you can see that it shows the date, and then also shows you the random number, right? So this is an example of a function that doesn't have input or outputs. Okay, so this is summary of different kinds of functions, the user-defined functions. You can have one input, one output, right? So if you only have one input, actually the bracket, the square brackets are not required. You can directly use area square equal this thing, okay? So you could also have, let's say, yeah, basically here you can directly use this line as the first line of the function file. You could also have two inputs, one output, right? Or more inputs, one output, right? This is a volume of box. We know that volume box is going to be height multiplied by width multiplied by length, right? So it could be one input, two outputs, like the circle function. You have the radius, and then it can calculate the area and circumference. And you could also have no outputs, right? So or basically you can create some plot, and then as long as you have the side, right, the length of each side, then generate a plot. It doesn't need an output. Okay, so this is an example or like a hands-on demonstration. This is trying to compute the distance traveled by an object as a function of g, right? And with an initial velocity of v0 and as a function of time. So let's just create this function here. So this is the drop function, and we don't necessarily need that semicolon there, right? So basically computes the distance traveled by the traveled and the velocity of the basically the dropping object as a function of g, initial velocity v0 and time t, right? So we know that the distance or the velocity is going to be g multiplied by time plus v0. And distance traveled is going to be half of the gt squared plus v0 multiplied by t. So this is I would say the results, right? You have three inputs and two outputs. Okay, so which means that let's say if you call the help of this drop function, so it has all of these descriptions over here. And then you could, I would say, run this function, right? So let's say that we defined certain A, right? The acceleration being 9.8, the initial speed being 10 meter per second, right? Time equals 5 seconds. And then we can define this whole set of variables, right? We have to edit it a little bit. Need to remove these signs and then bring them over here, right? So we basically forced this function to have all of the three outputs, right? And both of the two outputs, and then we also provided all of the three inputs. Okay, so the meter dropped is 172.5 and speed is 59. Okay. So here we actually defined all of these inputs here, but actually you can directly put in values like what we did earlier, right? So you could directly do it in this way. So A 9.5 or 9.8, right? And then I think we used 10 and 5, right? So you're going to get the same thing. And at the same time, since we define T could be a array, right? We can also put in an array here, right? 0, 1, 5. And then you're going to get the results, a meter dropped, right? Being an array over here, and then the velocity being an array. Okay. Um, so this is basically functions with multiple inputs or multiple outputs. So then we talked about the local variables a little bit earlier, right? So basically the local variable is only accessible inside the function. Once it's outside the function, once you export or output the results from the function, then all of the variables, local variables are erased, right? So as is mentioned here, the names of the input variables given in the function definition are local to that function. This means that other variable names can be used when you call the function. All variables inside a function are erased after the function finishes executing, except when the same variable names appear in the output variable list used in the function call. So what that means is that you could also define, let's say, G as a output, right? So we put in 10 here, but then you also sort of export this G value outside, right? So we could keep on using this local variable. Okay, so this is local variable, but we could also define global variables. So what if, let's say, you want some parameter to be recognized all the time in the same set of codes, right? So for example, acceleration, we're just talking about the acceleration on the Earth, right? So then what we can do is we can force the value of G being a global variable, right? So then what we need to type in is just global G, or we can create a new function, basically. Let's say function acceleration, right? So inside the acceleration function, we will define this global variable, G, and G equals 9.8. Save this file. So you can see that we define the G as a global variable in this function here, right? So then to use that G value, you could just type in global G, okay? And then it's going to automatically call the G or find out where the G was defined, which is actually from the acceleration file here, right? So you don't need to call that this acceleration file because this has already been defined as a global variable. Okay, so here now you can remove the requirement for the G, right? And then you see that now we didn't pass any value of the G. And if you try to, let's say, run this function again, now you don't need to type in G value. Okay, let me see. We need to first run this function because we haven't run it, we just saved it, right? So after we run this function, you can do CLC clear all the memory. So we first run this function and then run the drop function, or let's say drop, let's do 1 and 2, right? So you can see that we basically here we didn't define G. We only run the acceleration function, and now the entire MATLAB knows that there's a global value called G, and the G has a value of 9.8. So here we can just call the global G. So basically it's going to search for where we define the G, and then we're not going to use the G value because that's not an input. And you only put in 1 meter per second and 2 seconds, right? And then it's going to do the calculation. The reason why you only have one output is because we didn't force the function to give us two outputs. You could force it, right, to have A, B. Okay, so this is going to be the velocity and the distance traveled, right? Or the first is the distance traveled, the second is the velocity. Okay, so this is about the global variables, but at the same time, actually, the global variable is not recommended anymore. So if you move your cursor here, last time we talked about the code analyzer, right? You see this exclamation sign, right? So you see here, the global variables are inefficient and makes errors due to, let's see, diagnostics, right? So then basically it's giving you these warnings that these are actually not very helpful because it could be that here in this set of code, you're trying to calculate the gravitational settling of an object on Earth, but sometimes you might be calculating the gravitational setting on the moon. We're talking about, let's say, space missions, right? So then sometimes the G has the Earth's value, sometimes it has the moon's value, and you may easily get confused. And what's more important is that you may lose track of the acceleration file because right now we can still see it. But sometimes after you organize the files might be missing and you lose track of the file that actually define the value of G. And this is going to be a problem because if you cannot identify it, right, you cannot change it. So that's why the global variable now is not being recommended, and it's more, let's say, more being recommended in a way that you define the variables separately in each of your function. So basically, you just define G being 9.8 over here. Okay. So this is a global variable. And the next is a function handle. So this is again related to the, I mean, we can use the function handle for both the user-defined function and the built-in function. Basically, the function handle is just the at sign, right? So normally we use the at sign before the function name, and then you can use this handle to refer to the function. So for example, this is using we're trying to add certain function and try to find out the root of that function, which is f0. Okay, so we can know more about this f0 function later here. So here, basically f0 is, the goal is to find the zeros of a function. So you can use the f0 function to find the zero of a function of a single variable, which is denoted by x. So one form of this syntax is use f0 at function, and x0 is the initial guess. Okay, so you can see here, at function is a function handle for the function, and x0 is a user supplied guess for the zero. So it could be, let's say, we have a function of x squared plus x, or let's say e to the power x, right? And plus or minus 10, okay? So we want to find the root for this function. Okay, so if you look at this function, this is a non-linear function. It's not easy to find out where the root is, right? So if you consider the root, maybe it's close to 2, basically going to be between 2 and 3, right? So because if you put in 2 here, you're going to have a 4 exponential of 2, right? 2.7 to the power 2 is somewhere, let's say, maybe below 9 and larger than 4. It's hard to say, right? Maybe it's around 2. So then what we can do is we can define a function. Let's say function test1, right? We already defined test function of a variable x, and then this is y. And then we just name y as this function here. Okay, so this is our test1 function. And of course, let's say you can try to plot, let's say, this test1 function of 0 to, let's say, with a separation of 0.1 all the way to 3, okay? And then we can run the test1 function with the same x. So here, before we run it, we need to pay attention. Now we put in an array, right? If it's an array, then we have to use a dot, right? If you don't use that, then you are going to receive an error. So now we have this function here, and you can see this is how it looks like, right? It's going to pass over 0. And actually the root is somewhere, I would say, close to 2, right? Somewhere close to 2. But how do we find the actual root? So we're going to use the f0 function. So what you do is directly type in f0, And then we're going to use the function handle of at test1, and then give it an initial guess, right? So we know that the initial guess is going to be close to 2, or we can even do 1.9. And then we hit enter, it's going to give you the value here. Okay, so this is how we use the f0 function. You directly find the root of a function that basically it can be a nonlinear function or it can be a linear function. Okay, so one more thing that's quite interesting to test is you might want to see how it does this f0 function. It's actually using an iteration method. So how do we know it's an iteration? Because we talked about iteration before, it's for loop or while loop. The way we can know it's an iteration is just we can sort of unhide, right? We can sort of, let's say that remove the semicolon. So basically it means that every time it does this calculation, it's going to export the result. So now let's try this f0 function again. So you can see it's having all of these results here. Y again, y equals this, until you basically this f0 keep on exporting the y value, right? You can see that initially the guess is by putting 1.9, you have a y value of 0.29. And then it's sort of trying to converge this y value, right, until it's very close to 0. And then finally export this answer here, right? So using an iteration method to find out the solution of your function. Okay, so this is how we use the f0 function. So the f0 function returns a value of x that's near x0, right? So it identifies only points where function cross the x-axis, not points where the function just touches the x-axis. So what that means is that, for example, you have a function now x squared, right? We know that the solution for this function equals 0 is x equals 0, right? So we think that it's equal 0. So then let's try this, right? Because it's a parabolic function, right? Y equal x squared is a parabolic function. The only location that can lead to a y value of 0 is x equals 0. So now we can try, so we can even give it a very close value. And then it's saying that it cannot find the solution, right? Basically, the f0 function, in order to get the solution, you have to let the function go across the y equals 0 axis, go across this x-axis, right? So, for example, let's say this is another example, right? f0 at cosine, right? So we're trying to make the cosine function to be 0. We know that when cosine function is 0, it's going to be pi over 2, right? So then try it, it's pi over 2. Okay, and also, as you can see, the cosine function actually circles around the basically the center point of the axis, right? So theoretically, cosine function will also return the result of negative pi over 2, right? So the solution, another solution is negative pi over 2, but it's only reporting positive pi over 2. This is mainly because the initial guess you provided is close to the solution. Okay, so what that means is that if you have a function of multiple solutions, right, of let's say y equals 0, it's only going to look for the solution where it's close to the initial guess, right? So the example can be when you have a -2, and you can see that the solution is minus 1.57. It's minus pi over 2. So it's only going to look for the root when it's close, where it's close to the initial guess. Okay, so that's the sort of the limitation of the f0 function. Okay, so we said that the f0 can solve sort of sophisticated nonlinear function, right? This is another example. We can define this function of f1, right? f1, this is a nonlinear function, right? X plus 2 to the exponential minus x minus 3. So there's no way that we can solve it by hand. Okay, so if you see, I already defined this function here, and you can also sort of export it or plot this function. Plot, let's say, and then f1 with the same x. So you can plot it out. This is how it looks like, right? So you can see that basically it go across 0 when x is close to, let's say, 2.9 or 3. So then we could do F0 at, we have to use the function handle, okay? So if you don't use the function handle, it's not going to give you the correct result. You have to use the function handle and then give it an initial guess of 3. Then it's going to give you the actual value of 2.88, right? So if you see this function, it's actually close to that, right? 2.88. So you know it's not 2.9 and it's not 2.8. It's somewhere in between, right? So 2.88 is the correct answer. So remember in MATLAB or in Excel, we also showed this sort of the capability of solving the nonlinear function, right? Remember at that time we were saying that it's using um, the iteration method to find out the final solution, right? We call that method as the goal seek. So I can quickly show here again, right? So we sort of define x and y, and then x, we can use a value of 2 in the beginning, and then y equals x plus, no, it should equal to this value plus this value, no, plus 2 multiplied by exponential of this value, or minus this value, minus 3. So you can see by using different x values, we're going to get different results, right? So we said that to solve this, to set y to be 0, we could use the what if analysis and goal seek, right? So we set this cell to the value of 0 by changing the cell of x, okay? So you can run it, and then you can see this is the result 2.89, right? So this is the goal seek that can achieve a similar, sort of a similar functionality or similar goal, okay? So you can see that it's quite similar to MATLAB. And you may say, well, what's the advantage of MATLAB for doing this? The advantage is that you can solve like a whole set of functions. Remember, for the goal seek here, you have to do it one by one, cell by cell, right? But in MATLAB, you can just type in let's say the solution, the F0 function, you can solve it, let's say using a for loop, using a while loop, you can solve a whole set of functions, right? Very fast. So you don't have to do this point by point, let's say goal seek in Excel anymore. Okay, so this is how the result looks like. This is a plot. And as you can see, there are actually 2 roots from the plots, right? So which means that when you use a different initial guess, let's say if you use 0, right, it might be looking for, eventually look at or find out the root to be on the left side, right? So the result of the F0 depends on the initial guess. And actually, this is almost the same for all of the MATLAB solvers for these different sets of functions, right? So basically, you can see that if you find a more precise value of the 0 near x equals minus 0.5, you can see the answer is this value, okay? So still regarding the finding the solution of a function, right? F0 finds a function of 0 of a function of a single variable, right? So then you may have the question, well, what if we have a set of functions, right? Let's say the function involves x, y, and z. There are 3 nonlinear functions, right? 3 variables involved. Are there ways to solve these more sophisticated equations or sets of equations? Actually, we'll use the fsolve function. So the fsolve function will find the 0 of a system of functions that involve, let's say, x, y, and z, or all the way, let's say, even 10 variables or even more variables. Okay, so it actually uses a nonlinear solver, and its functions can be both linear or nonlinear. So the syntax we can use is just f0 or fsolve at the function and the initial guess. It's very similar compared to the f0 function. And the other thing is that you remember F0, the function has to go across the x-axis. It's not the same for the fsolve function. So overall, the fsolve, I would say, is a better function that can solve more sophisticated sophisticated sets of functions, but also needs a longer computational time, right? So if you know that your function just involve one variable and it's a simple function, you should use F0. But if it's more sophisticated functions, we should use fsolve. Okay. So here are a few examples, right? So then, for example, here, um, we can use the F-solve to find the solution of this system of two equations, right? The first equation you can see is e to the power of e to the minus x1 plus x2, and then there is x2 and x1. So basically, with this function, you cannot find the analytical solution, right? It has to be a numerical solution. So to solve this function, actually the f-solve function, it only take in one variable. So for example, let's say when we first define this function, right, it has to be putting in one variable, which is the x value, right? So we have to convert x1 and x2 into basically x sort of the x1, the first element of the x array, right? And the second element of the x array. And basically, we need to first rearrange this set of function. We need to define, let's say, y equals this thing minus this term, and the other y, let's say y2 equals this term plus this term minus 1 over 2, right? So this is how we can define it. The function f equals root. Say this is how we define it. And then we can save the function. Okay. So basically over here, right? So you see that we define this function root 2d. It can be any name. Okay. So you can see that the first result, the first return or first output, I would say the only output, but the first element of the output is just the difference between the term on the left and term on the right, right? And then we also change the x1 into the first element of x, x2 to the second element of x. Okay, so you can see that's exponential of minus exponential minus 1 plus 2, and then minus x2 multiplied by, so basically this is a sophisticated equation, nonlinear equation too, right? So then f2 being x1 cosine x2 plus x2 cosine x1 minus 0.5. So this is how we define the function. Now we just need to make this function to be 0. But remember, instead of setting or using the function of f0, here we use the function of f-solve. Okay, so then we can just type in f-solve. We can use x equals f-solve, or it can be a. It doesn't really matter what we give to the final solution. Okay, so f-solve, and then we use the function handle of root 2d, and then we need to give it the initial guess. And the initial guess, we can give whatever we want, right? So let's just give it a 0 and 0, okay, or 0 and 1. It doesn't really matter, but try not to give something crazy, right? If you give the initial guess to be really, really far away from the actual result, then it could be that it takes a longer time to eventually find the actual result, right? So then you can type in, and then basically this is AA, right? X1 equals 0.35, X2 equals 0.6. Okay, so you can see that the f-solve is overall a more sophisticated function that can solve sets of equations. It's better overall. It's better than the f0 function, right? And you can see that it also involves iteration, right? Eventually, it involves a stopping criteria, and you can actually change the stopping criteria by using the options in f-solve. So you can do, say, help f-solve. You can see that the f-solve actually you can choose different options. Right? Options, there are optimization methods, options, right? So basically you can choose basically different types of these options, and eventually but overall their results will be actually quite similar. Okay. So this is an example of two variables, right? And we have two equations, and we can get the solution. What if we have three variables, right? So here we actually change the function to linear, but it doesn't have to be linear. It can be totally nonlinear, right? So then we can create a new function. Let's say we call it function root 3v, right? Three variables. And then we have the equation of 3x plus y minus z equals 2. So remember, the first thing we need to do is we need to convert these variables to different elements of x, right? So we name x as x1, y as x2, and then z as x3, right? So you have 3x1 plus x2 minus x3 minus 2, because the goal is to set this first equation, this term here, right, this function to be 0, right? And then f2 is going to be x1 plus x2 plus x3 minus 6. And then f3 is x1 plus x2 minus x3, right? So this is our set of equation. And then we could just use the fsolve, right? So function handle root 3v, and then give it an initial guess, 0, 0, 0. And then you can find out that the solution is just 1, 2, and 3. Okay, this is a quite simple solution. But if you have sophisticated function, you can also put it inside. So now you can see how MATLAB is more advanced compared to Excel, right? Because for Excel, there's no way we can solve for a set of equations, right? So actually in engineering, especially later on when we talk about the matrix calculation, right? So we're going to sort of introduce a little bit more about these fsolve function and then some other additional functions that involve the system of equations. Okay, so that's the f0 and fsolve. I would say overall, we will probably use these functions quite a lot later on as well. So similarly, you can find the minimum of a function, right? So earlier we tried to find the, let's say, the 0 of a function. We can also find the minimum of a function. So the function is the f function minimum boundary, right? So the f minimum boundary function finds the minimum of a function of a single variable, which is denoted by x. So you use this syntax here. So x1 and x2 are the boundaries, right? So within this boundary, which value of the x will give the minimum value of this function? Okay, so basically here where the function is the function handle for the function, this function returns a value of x that minimizes the function in the interval of x1 and x2. So for example, the cosine function, we know that when the cosine function has the minimum, naturally it needs an input value of pi, right? So if you just type in this command here, right? So we're trying to find the minimum, basically the x value that gives the minimum of the cosine function. You'll find out that it's just pi value, right? 3.1416. So when using this function here, it's more convenient to define the function in a function file. For example, you have this function, then you just define the y equals, let's say 1 minus this thing, right? And then to find it, you call the function using the function handle, right? It will return you the value. And then after you find this, let's say the x value that give you the minimum, and to calculate the minimum, you just use f2 of 1, right? You get the result. Otherwise, let's say if you don't define it as a function, then you have to type in all of these equations again. Okay, so overall, it's better to define your function earlier before you do the calculation. Let's say we can type in this example here and define this f2 function. And then let's try. So the goal is to find out the x value between 0 and 5 that give you the minimum value of this function, right? You can see that actually the minimum value or the x value that gives the minimum result of this function f2 is at 1. So is it really at 1? We can make a plot, right? So it's 0 to 0.1 to 5, and then we can do f2, the same thing. So this is how the function looks like, and then you can see that the minimum is indeed at 1, right? So then how do we find the minimum? Then we can just do f2 of 1 because we already found out the x value that give you the minimum function results, right? So then it's going to be this value here. It's always better to save your function as a .m file, as an m file, okay? So a function can have one or more local minimum and global minimum, right? So the same thing, we're talking about minimum, but we can also find out the maximum, right? So it's just using the same thing of find maximum, right? Or you could also just find out, let's say, the minus, right? Or the, let's say, or you can define a function that's a reflection of your function, right? So in this way, you can find the maximum result. So basically for this function here, the function can have one or more local minimum and global minimum. So this function is only going to help you find the local minimum, right? So it's not going to give you the global minimum, and that's why you have to give a specific or a wider range for the function. So for example, if you have f2 and then you're only going to look for the minimum value between the range of 2 and 5, then it's just going to tell you, hey, the minimum in this range is 2, right? But actually, we know that the global minimum is happening at 1, okay? So another example, right? So you could have a function of this polynomial, right? So this function has one local and one global minimum. This is a local minimum, this is a global minimum. So on the interval of 1 to 4, then it's actually going to give you the local minimum of 1, right? But so to find the global minimum, you have to maximize your range a little bit. And how to find out the correct range, right? It's better to make a plot, right? If you make a plot, then you can find out where the minimum is located at. And we know that this is a nonlinear, the polynomial, and then it's difficult to find the analytical solution directly. So that's why if you use MATLAB, then you can directly find out where the local minimum or the global minimum is located at. Okay. To find the minimum of a function of more than one variable, we could actually use the fmin search function. So one form of its syntax is here where function is the actual function and we're using the handle, and then x0 is the guess that's supplied, right? So for example, you could have a function that has two variables, x and y, and then we define the m file, and then we just, again, similar to the fsolve function, you cannot directly put use x and y. You have to name x as x1 and y as x2, right? So then this is our function. Just type it in, copy it inside the function here. Okay, F4. And then to find out the local minimum, or let's say the minimum of this function here, then you can do f minimum search. And then you're going to have the result of minus 0.7 and 0. Basically, the minimum or this local minimum occurs at this location. Okay. So these are, I would say, some functions for finding the solution, finding the minimum, local minimum, global minimum. So why do we need these functions? On the one hand, we can use these functions to solve problems, right? Because solve equations, because in the, let's say, the environmental engineering, people are interested in the location where let's say, the BOD value or the organic chemical concentration is the minimum or is the lowest, right? So how do we find the lowest point? Okay, so of course there are analytical solutions, but if, let's say, there are more sophisticated systems that we cannot find the analytical solution, then we will use these functions to find the minimum. Or we can also find out, let's say, at which time the BOD level reach to a certain level, right? So let's say the BOD or organic concentration reach to 1 milligram per liter. If you have the model, and then you can just list the BOD equation and minus 1 milligram per liter and set that to be 0, right? If you set that to be 0, then we use F0 function or the fsolve function. And if it involves a system of functions, then we'll use the fsolve function, okay? So then here I'm introducing different methods for calling the functions. There are overall 4 ways to invoke or call the function. So these are as a character string, identify the appropriate function M file as a function handle, as an inline function, or as a string expression. We're going to talk about these one by one. Okay, so examples of these way follow the F0 function used in the user-defined function that we had earlier. Okay, so the first is as a character string, identifying the appropriate function M file. Let's say we define this function. Okay, so as function 1. Okay, so we can save this function also, function 1, right? So we can use the F0 or Fsolve. Right, so here instead of at the function, we could also just type in the string function 1 and then 0 to 3. Okay, so it's going to have the solution, right? Show you the solution, which is 2, because x squared equals 4, you know the solution is 2 when it's in the range of 0 to 3, right? So you could type in the string, right? Type in the character string, or you could directly call it by using the at, right? It's also 2 here. So that which is the sort of the script that we use here as a handle. Or you could use it as an inline function object. So what that means is that we actually can define this function in the command window. So you can define function 1 as x power 2 minus 4. So you can see that the function here is basically a string, right? And then function inline is we actually call the inline function here, function 1. Okay, so we define an inline function. So basically, the inline function is not going to define as a .m file. So people sometimes use this because, so for a function that's this easy, maybe you don't need to define a .m file, right? You can directly type in and find out what's the solution. But if you're talking about a system of function like this one, or I remember it was function 2, let me see, or the root 3v, right? There's no way that we can define the function just by using the inline function. Okay, so if it's a simple function, you can use this inline function, and then you can try F0, and then directly function inline, and then give it a range of 0 and 3. Okay, so this is using the inline function. Okay, this is sort of something new, but it's also kind of uncommon. Okay, so eventually you can also do the string function. So remember we defined this function 1 earlier. You can try directly type in, let's say function 1. Okay, instead of using inline, converting to inline, you can directly type in the string as well. So overall, there's also a comparison. So the function handle method is actually the fastest method because you define it as an M file. It's already in the directory. The computer is going to directly read that file, right? Instead of reading in all of these strings. So in addition to the speed improvement, another advantage for using the function handle is that it provides access to subfunctions, which are not visible outside their defining M file. So what that means is that if you define this function 1 over here, right? So you could actually call this function from another function. Right? You don't need to type in these functions anymore. So let's say define a test function, right? So inside the text function, we can call this function 1, which is function 1 with a value of 3. Okay, so you can define this as z. Okay, so we save it and then run it, right? So we can directly run this function, although this function calls the function 1 here. But this is good, right? Because we already save it as an .m file, so we can directly use it. Okay, so this is the different methods of calling the function. So then the next is the different types of the user-defined function. So there are actually quite many different types. So here we're just going to talk about, let's say, 3 or 4 types. So the first type is the primary functions. The primary function is actually what we already typed in here, right? So these are called the primary functions. So the primary function is the first function in an M file and typically contains the main program. Following the primary function in the same file can be any number of sub-functions, which can serve as subroutines to the primary function. Okay, so then usually the primary function is the only function in an M file that you can call from the MATLAB command line or from another M file function. You invoke this function by using the name of the M file that's defined, right? So we define f function one, and then we can call function one. We normally use the same name for the function as file, but the function name, if the function name differs from the file name, you must use the file name to invoke the function. Okay, so if they're different, then you should use the file name because this is how MATLAB search for the functions. So the second is the anonymous function. So anonymous function, basically, you don't create an M file. Okay, so it enable you to create a simple function without needing to create an M file for it. You can construct an anonymous function either at the command line or from within another function or script. So what that means is what we have done over here, right? So when we define this function here, right, this only exists in the command line. Actually, you cannot directly call it from the from any code or from any functions that we define. And if you close the MATLAB program and open it again, the function is gone because this is not saved as an .m file. Okay. So then the next is the subfunction. So the subfunction is placed in the primary function. So actually in these functions, we can further define subfunctions. Okay, so basically the subfunction, we can call the subfunction from this main function. So for example, we can define a subfunction of, let's say, the function of being x multiplied by x1 multiplied by x2, right? And let's say we name that as a product, right? So we can directly call this product function inside this main function. Okay, we're going to give an example later on. Okay, so first, anonymous function enable you to create a simple function without the need to create an M file, right? So the advantage basically is if you have a very simple function, you don't necessarily have to create an M file to sort of save as that function, right? If it's just as simple as x squared minus 4, you can define it directly inside the command window. So the way it works is that the function handle is going to be at the argument list, whether you have one input, two input, right? X or Y or Z, or you're going to be is A or B or C, right? So the argument list, and then the expression, which is the equation that includes the X, Y, Z or A, B, C. So this is an example. You can define a function called SQ. Okay, so SQ equals, this is argument list, right? X, and the function is x squared, right? So we already defined a function which is saved in this way, right? So then, well, we can do it in a different way. Let's say that it's x squared minus 2, right? We define this function. Remember, we can do f0, right? And then we can do at square, and then try to find out the solution for the function, right? So then it looks like here we cannot directly use this function, right? So let's try SQ. So without using that handle, because you see the output is already a handle, right? So it doesn't need that at sign anymore. So you can directly use that function and then, because this is function handle, right? And find out what is the solution. So to improve the readability, you may enclose the expression in the parentheses, right? Because we typed in something like x squared minus 2. You can put everything in the parentheses to sort of note that this is the function. And also the space between the x and the at sign doesn't matter. So it's always going to be the function that's following this at x here. Okay, so you can try, let's say you have call this function and give it an array of 5 and 7, then it's going to return you the x squared minus 2 by inputting this array over here. Okay, so you might think that this particular anonymous function will not save any work because typing in require 9 keystrokes, one more than it's required to type this thing. However, the anonymous function protects you from forgetting to type the period required for any exponentiation. Right? Anonymous functions are useful. However, for more complicated function involving numerous keystrokes. So then you can also pass the handle of the anonymous function to other functions, right? So for example, this is what we tried just now. We define the function of x squared minus 2, and then you can find the minimum, right? So if you're not going to use that polynomial again, you can omit the function handle and define the function directly typing this way. Okay, so basically, let's say you don't want to use the poly one anymore. Okay, so if there are multiple arguments, you can also use this function anonymous way to create a function, right? So then it's going to be a similar result, right? So multiple arguments, and you can directly call this function with a value of 3 and 4. You're going to get the result of 5. As another example, consider the function defining a plane, right? Z equals ax plus b. The scalar variables a and b must be assigned values before you create a function handle. So for example, a and b, right? If you use a and b, then they have to be assigned, right? So z is this way. So you could also call the function, like call one function within another. So what that means is that you can basically call the function of, let's say f, you define the f here, and g is sine of x, right? So you can call the function of g, which is the fx. You're using basically f inside the sine, right? So it can be loop by loop, and eventually you can get the result, right? So I would say for more of these more sophisticated functions, it may be better to just create your .m file, right? Because it gives you a clearer way of how the function goes. Because otherwise, if you just type in once, it's okay. If you are going to use it in the future, it's always better to create the M file, including all of these functions. Okay, so variables can appear in an anonymous function in two ways: as variables specified in the argument list, right? And as variables specified in the body of the expression. So for example, variable a and b that you have to define earlier, right? So this is basically overall the anonymous function, right? So the difference is that we actually don't involve any M files when we define these new functions. So the next type of function is the subfunction. So subfunction basically it's a part of the primary function, right? So a M file may contain more than one user-defined function. The first defined function is a primary function whose name is the same as the M file, and all the other functions are called subfunctions, so which are the functions below the main function, the primary function. The subfunctions are normally only visible to the primary function. Okay, so however, this limitation can be removed, but most of the time it's only being used inside the primary function. So we can actually have a example, right? So for example, we are defining this subfunction demo. Okay, so subfunction here, this is the main function, right? That equals a minus mean of a. So then we define this a. So you can see that the mean is a subfunction that we define over here. Okay, subfunction w of mean of x, right? So actually the mean is different compared to what we calculated. So this is actually going to be a geometric mean, right? This is not an actual arithmetic mean. This is geometric mean. So then it's square root of the summation squared divided by length of the x, right? So it's a geometric mean. So then if you type in 4 minus 4, right? The geometric mean is already 4, and this is what you get. But then if you directly call the function of mean, it's going to use the MATLAB, let's say the predefined, right? The built-in function of the mean. Okay. So then you're going to get completely different results. And this is mainly because when we call this function, it's going to first look for the function or the sub function that's defined in this main function here. Okay, so you can sort of see the sequence for the function definition. So when we call the main function directly in the command window, it's going to first look for the built-in function, right? But when we call the user-defined function, then it's actually not going to look for the built-in function, but the sub-function inside the primary function. Okay, so this is related to the precedence when calling functions. So the order in which MATLAB checks for function is very important. So when a function is called from within an M file, right? So if it's inside an M file, the MATLAB first checks to see if the function is a built-in function, such as sine, or if not, then it checks if it's a sub-function in the file, right? Then it checks to see if it's a private function, which is a function file that's inside the private subdirectory. So we are not going to talk about that in this course. And then the MATLAB checks for standard M file on your search path, right? So you can see that basically it first search for the built-in function and then search for the sub-function. And because of that, because MATLAB checks for a subfunction before checking the private and standard M file function, you may use subfunction within the same name, with the same name as another existing M file. So what that means is that if you have another file within the directory called test.m, and you can create a function called test. Okay, so because when you run this function, it first look for the subfunction and then go to the directory. Although it's always not recommended to use the same function of the name, also because we want to avoid confusion for the users, right? Both for the coders and the users. So this feature also protects you from using another function unintentionally. Okay, so we can probably go through this example here. So what I'm trying to say here is basically you define a function inside a function, right? So we define this mean here, but at the same time, actually mean function, this is a built-in function. Let's just define a new function, geometric mean, right? Mean geo. Then we can do mean geo. Okay, so this is the geometric mean, how we define this function. And basically here, this is a primary function, this is a sub-function. So whenever we call this primary function, it will first look for, hey, where is this function, right? It found out that this function is located in the primary function. It's directly going to use this one, right? And then at the same time, when you define this mean geo, it cannot be accessible from outside the function file. It's sort of like a local variable for the function. Okay, so then you can try, let's say, sub function, and then we can do -4 and 4. Okay, so this is our result, right? So basically have -4 and 4 minus this geometric mean, which is 4, right? Close to 4. Okay, so and then if you try, let's say mean geo, right? And then -4 and 4, you can see that basically it cannot be recognized because we did not save a .m file for this function. Okay. So this is our example, and then so basically because of that, the use of the subfunction enable you to reduce the number of files for you to define your functions, right? So I think that's it for this class. So this class, we talked about the user-defined functions. There are quite a few example problems, right? So we talked about the inputs and outputs for user-defined function. You can have multiple inputs, multiple outputs, or no inputs or no outputs. We talked about the function handles, which is the @ right? We used this function handle to find the roots of functions. We talked about F0, fsolve. We said that fsolve is more powerful. It can help us solve a set of nonlinear equations, right? And also try to look for the minimum of a function, right? By inversing this function or doing the reflection, putting a minus sign of that function, you can also find the maximum. So then we talked about the methods for calling the functions. The easiest way or the fastest way is to define the function as the .m file. And then additional types of functions, anonymous functions, right? So we don't define a .m file or subfunction, which is sort of the additional functions within the .m file, right? So that's it for this class. So we talked quite a lot about these different types of user-defined functions. So I will also include some practice problems from these, let's say, by using these functions, right? Especially regarding solving different sets of functions by using fsolve. And just feel free to let me know if you have any questions. Thank you. Bye.